this. Okay, so again, welcome everyone. Today, our speaker is Petitt from Politecnico di Milano, near my office, and he will tell us about the well-posedness for large solution of the porous medium equation in RD. So, Troy, I leave you the stage.
Okay, thank you, Lorenzo. Thank you for everybody in attendance. Okay, so let's get to the first slide. So we're talking about the Koshi problem, RD. Here we are. Diffusion. So we have some sort of linear or nonlinear second order operator here. Could be the Laplacian, in which case one becomes the Koshi problem for the heat equation. Or it could be, as we study, the porous medium equation. So A of u is the Laplacian of u to the m for m strictly greater than 1. And you could also take fractional pseudo-differential operators, different operators, even, as far as I know, you can even take reaction diffusion operators. So the game is to figure out how big you can take the initial data so that the equation is that the equation is well posed. So if you think about the one-dimensional heat equation here, you might think, well, how can a diffusion equation not be well posed? Because diffusion equations automatically smooth things, automatically kind of shrink. You would think they kind of shrink the initial data, but it really only works for small initial data. And you can look at the second spatial derivative, for example, of this green function is negative. So that means that the function is going to be decreasing. And that's in general what happens for small initial data. Initial data belong to L1 for the heat equation and for other diffusion equations. But what happens is if you take a large initial datum, diffusion actually works against you. It's going to blow up the initial data. And it could even blow up at finite time. For example, the heat equation, you have a representation formula. So every non-negative solution, this is a classical theorem from the old days. Every non-negative solution is necessarily written in that form. And also you have kind of the dual result, which just says that if you have an initial datum integrable with respect to the Gaussian kernel, then the solution is well defined. Although if you have critical growth, like e to the constant x squared, if you have critical growth, this solution will blow up in finite time, and you can calculate the exact time because taking advantage of this convolution formula. So that's kind of the game, and the types of results that we're looking for. I've kind of already hinted at this. You want to find a class of initial data, which is going to be data that's growing at spatial infinity, so that inclusion in this class of initial data gives rise to a solution. And the dual problem, which I haven't really looked at that much, but it's very, very interesting, is this Witter result, to show that usually you have to assume that solutions are positive. You say positive solutions have necessarily an initial trace satisfying whatever condition describes the set M. And then you also have to show uniqueness, both of given one initial trace, you have to show obviously one solution, and also given one solution, you have to show that there's only one initial datum. So to put these in bijection. And then another interesting concept is to find the subset of the class of initial data for which global solutions are guaranteed. So very simple, just the Koshi problem in RD, and it's extremely simple. The only thing that you have going on is the initial data, the size of the initial data, and how fast the diffusion operator can diffuse. Okay. So now let's go to slide number 2. Okay, so in particular, we're going to talk about the porous medium equation. So I mentioned it already, ut equals Laplacian of u to the m for m strictly greater than 1, the Koshi problem. And to get a sense, so it's just not symbols, get a sense of what this thing really is, we expand the Laplacian into the divergence of the gradient. And you can just take the gradient of this function, and you get m times, well, the m can be scaled out by rescaling in the time variable. So it's just divergence of u to the m minus 1 times the gradient of u. And this is a classic quasi-linear degenerate parabolic equation. And it degenerates because this diffusion coefficient, when u is very close to 0, the diffusion goes to 0. So basically, if the solution or the function is close to 0, that means that no diffusion happens, independent of the local character of the function. And likewise, if u becomes big, there's lots of diffusion. And you can see on this graph here, so you have not so much diffusion here because u is very small. You can look at this equation here, regardless of the curvature of the function. And here we have that there's a lot of curvature, and also u is very large, so you have lots of diffusion here. So you can see that as opposed to the heat equation, solutions of the porous medium equation may blow up in finite time, even for power, for initial data growing at a power rate. And so in order to understand the behavior of a generic solution to the porous medium equation, let's say, it's a good idea to study the source solution. And you can think of this as the heat kernel, nonlinear heat kernel. So it's just a weak solution to the porous medium equation, where you take the initial data to be the direct delta centered at 0. And you look at solutions. In fact, both for the heat equation, obviously the Gaussian, and also for the porous medium equation, we have an explicit solution. C and K, kappa, are both explicit. Gamma 1, lambda 1, and lambda 2 are constants that are very closely related to the scale invariance of the porous medium equation. And you notice, what does this function look like? You fix some positive time, and you kind of ignore all the constants. What does it look like? It looks like an inverted parabola. That's the positive part of an inverted parabola. So remember, this is the solution that converges, the weak solution that converges to the direct delta when you take time going to 0. So this is a real weak solution. Oops. And you can study this source solution to find properties of the porous medium equation. Number 1, finite speed of propagation. The heat equation, on the other hand, has infinite speed of propagation. This means this comes from the representation formula, integrating with respect to this Gaussian, which is positive everywhere. This means that for the classical heat equation, you start with initial data that is compactly supported. For all positive time, this heat equation is somehow diffused heat everywhere. Only a tiny bit, but still you have this infinite speed of propagation for the heat equation. But you look at this, the porous medium equation, solutions to the porous medium equation have this free boundary. And you you can estimate the speed of the expansion of the boundary. And likewise, it's basically the same property is that you have a lack of C infinity smoothness, because on the boundary, there's no way you have this is a C infinity function. So you can say weak solutions of the porous medium equation, not C infinity. And just as in the case of the heat equation, these source solutions, these heat kernels, are going to control the asymptotics of solutions as long as the initial data belongs to L1 in some smallness class. And the subject of the talk is to talk about the optimal well-posedness. And so the point here is that the source solution not only has all these properties, it also gives you very important information about how big this class of initial data can be. So that well-posedness is guaranteed, even in a nonlinear setting where you don't have a representation formula. Okay, this one. Okay, so now it's time to do a little bit of math. Not too much. Okay, so I'm going to talk about this this method from the 80s by these three mathematicians about how to show existence, and really optimal existence. Optimality was proven in a different paper, but the existence, which is saying initial data belonging to some norm space, necessarily gives rise to a local and time solution. So how do you do this? You have to start by defining the appropriate norm spaces. And how do you interpret this? Well, it is, first of all, R is a fixed positive constant. R is fixed here. So what's going on is you're ignoring the behavior of the function close to R. I mean, close to the origin. So in a ball of radius small r, you're ignoring the behavior of the function. All you care about is the tail behavior, which makes sense. If we're looking for an integrability condition, all we really care about is the tail behavior of the function. Also, under the basic condition that all of these solutions are locally L1 in order to define a distributional solution of the porous medium equation. So what's going on here? We have r to the minus d. This part cancels with the growth of the ball itself. And then we have this minus 2 over m minus 1. And this is saying that in an L1 sense, solutions, initial data cannot grow faster than big O of the norm of x to the power 2 over m minus 1. So it can't grow faster than a fixed power rate. And so we have to define an L1 norm and an L infinity norm. And these are kind of like, you can think of these as sort of like weighted L1 spaces. So we have these norms, and we have to prove a priori estimates in these norms. So these are the estimates we want to do, especially look at number 3 and number 4. Number 3 is a L1 L infinity smoothing estimate for initial data belonging to these big classes. So it's not really L1, it's these big norms, but you still have L1 L infinity. So this is saying for all positive time small, obviously the solution may blow up at some fixed positive time. But for small time, no matter what the initial data is, as long as the initial data belongs to this class, and as long as this norm is finite, the solution is going to is going to belong to the L infinity version of these big norms. And that's a L1 L infinity smoothing estimate. And then we have this L1 contraction estimate. Some people call it different things, but I usually call it L1 contraction, saying, okay, if you take two initial data that are close enough to each other, the solutions don't diverge too much from each other, at least for a small time. So this constant obviously is blowing up in a big way. But still, for local time, you don't have too much divergence. Okay, and so let's see, the main strategy here is to, so this is the green part down here. You take an initial datum belonging to this class. We call it X, the locally L1 functions, such that this norm is finite. So you take initial data in this class, which is going to be, at least in an average sense, growing with a fixed power rate at spatial infinity. You truncate the initial data, you cut it off at a certain height, you cut it off outside of a certain ball, so that the initial data u sub 0, comma n is in L1 and it's in L infinity. Once you have L1, L infinity initial data, the theory, the well-posedness theory is already known, and you're guaranteed a semi-group solution. So now you take the semi-group solution and you try to prove these estimates in these big spaces. And then in the end, you're going to pass to the limit and the truncations to get that these estimates are also valid for the actual solution. And then this estimate number 4 is very important for regularity. I mean, for existence, because remember, we're truncating the initial data, and we're going to put these truncations into this estimate, and we're going to show that. Well, I mean, these people showed this 30 years ago, 40 years ago. But you put these initial data into this estimate. You have to show that the initial data, that this series of truncations is a Koshi sequence. Therefore, at least for a small time, the semi-group solutions corresponding to the truncations is a Koshi sequence. Therefore, by the completeness of this norm space, which you have to, there's nothing to prove, you get at least some limit object. And usually it's not so bad to show that this limit object is also a solution. So that's why this estimate here, number 4, the L1 contraction estimate, is really critical to show existence, at least for local existence. Okay. But in order to get to these smoothing estimates and getting to these contraction estimates, you need to prove this key estimate here, where it's easy to show that bounded solutions satisfy this star property here. And then you have to prove this green box. And I'm going to sketch the proof of this green box here. So what's going on? It's basically the same as the smoothing estimate, but it's a previous step. So initial data belonging to L1 give rise to solutions belonging to L infinity. Okay, so we're going to try to prove this using the Moser iteration technique. So I'm just going to say a few words about Moser iteration in case you don't know, because it's a very nice method of increasing regularity. If you want to show that a solution is L infinity, you can try to use a Moser iteration. So the classical Moser iteration comes from the theory of linear elliptic PDEs with rough coefficients. This was solved by De Giorgi in the 1950s, the Hilbert's 19th problem. Moser, a few years later, gave a different proof, which is this. You can see this method is also can be easily applied in its original context to the elliptic equations, linear elliptic equations. Okay, so what do? So you take phi to be some smooth function, bounded or whatever, cutoff function, type function. And okay, then you expand, here we expand the Laplacian. And then we apply star on the first term. So I applied it already. You replace Laplacian of u to the n minus 1 by this minus lambda. And then you test this differential inequality by a power of u of the solution. So this is the key idea of the Moser iteration, at least the first part of the Moser iteration. You're testing the equation with the solution of the equation raised to some power. And then you get certain terms disappearing because of estimates on, for example, this one, you have estimates on cutoff functions and stuff like this. And you can end up showing, so you look here, you can, you integrate by parts, you test the partial differential inequality with this function, you integrate by parts, and then you have an energy inequality, you have an energy estimate, and on an improved norm space. And then when you apply Sobolov's inequality, you have, I wrote it in green, a gain in integrability with respect to the right-hand side. So now you can control a higher integrable, a higher norm of the function with by a lower norm of the function. So this is a gain in integrability, very important. And then you iterate this. So you can take any p. You can take p equals 1. This is what they do in this Moser iteration. You take p equals 1, and then suddenly using this Moser iteration technique, you have an L1 to L S plus S times M minus 1. That's S times M, where M is positive, M is greater than 1. So you're passing from the LP norm to the LSB SP plus B norm, where this is bigger than P. And then you iterate this over and over and over again. And you have to be very careful about this constant appearing on the right-hand side. When you do this, you end up with something L infinity. So you iterate P sub J to S times P sub J plus B. S being the improvement coming from Sobolov's inequality. You iterate this process forever, and then you get something like this. Obviously the details are the details, and they go on for many pages, but the idea is, in the end, you control the L infinity norm by the L1 norm. You have 1R here, you have L infinity R here. So that's a huge improvement. And this comes from Moser iteration. First, you test the equation with a solution, with the solution of the equation. Then you use Sobolov's inequality to get a gain in integrability. And then you iterate this process all the way to infinity. So this is how you prove this L1, L infinity smoothing estimate. And 3 is just a consequence of 1 and 2. And it's a consequence of this pointwise estimate, the Aronson, well, here's what it's called, the estimate, the pointwise estimate on I think this is called the pressure. Some physics thing. Okay, so maybe like 5 minutes or so. So I'll try to say a few words about asymptotics, just to give a really general idea. Okay, so keyword here is large solutions. So just as in the case of the heat equation, and apparently in the case of these wave equations, small initial data converge to the source solution. That's known. For example, if you take the heat equation, initial data belonging to C infinity compactly supported converges to Gaussian. However, if you take large solutions, these are initial data still bounded, but decaying too slowly to belong to any, at least to belong to L1. Then you get a different asymptotic behavior. And so there's a lot of details, but the key idea, which may be useful in other contexts, is you want to use the scale invariance of the solution, scale invariance of the problem, the natural scaling of the porous medium equation. And so you know that if u, say u of xt is a solution to the porous medium equation, then u of k for any positive parameter k and any smooth enough function f of k is another solution of the porous medium equation with a different initial datum. Okay. And the idea is you want to know what happens for a large time for these large initial data. So what do? You rescale the initial data. You rescale the solution at the same time. And then, so you construct this family of solutions uk with initial data u sub 0, comma k. And then you pass k to infinity. And we rig the system so that u sub 0, comma k converges. The interesting case is it converges to the singular initial data. Okay. So we fix things so u sub 0 converges to the asymptotic profile that we want it to. And then we have this series of solutions, this family of solutions u sub k, and then by compactness, a priori estimates and compactness, it converges to something u sub u hat. And here there's a lot of trickiness going on here. So k is something where time is involved. Time is involved in a very subtle way, but so in the end, it's you want to know obviously how the function behaves for time as time goes to infinity, and then you have u hat and u sub alpha, and u sub alpha is the solution, usually explicit or self-similar, corresponding to the initial data phi sub alpha. And you have to show as a last step that these some sort of uniqueness theorem for initial data that are singular or that are a Dirac delta. And so that's sometimes a subtle step. So as I said, functional analysis says that you can find a limit solution, and usually it's easy to show that this is a distributional solution just because of how how weak a distributional solution is. And then you have to show that u sub alpha and u hat are actually the same function. This is a question of uniqueness in this class. So I guess I didn't really have enough time to explain this asymptotics idea that well, but the take-home message is that for large initial data, you can rescale. Basically, you can find the asymptotic behavior of solutions by rescaling the solutions and rescaling the initial data in such a way that that the initial data converges to the initial data of the solution you want to show that the function converges to. So that's the idea. And that's all I have. You can ask me any questions you want.